Welcome to the e-lecture session for diploma students. In today's session, we are going to deal with the various types of DC generators. DC machines have been broadly classified as three major categories. One is the permanent magnet category, the second one is separately excited generators, thirdly self excited generators. The definitions and the characteristics of separately excited generators and self excited generators were dealt in the previous class. Let us go on to the further classification of separately excited DC generators. It is further classified into voltage excited and current excited generators. Again, the self excited generators are classified into series generator, shunt generator and then compound generators. This compound machine has further been classified as long shunt generator and short shunt generator. Based on the connection, it is further classified into cumulatively compounded and differentially compounded generators. Now, first we will deal with the separately excited DC generator. Separately excited DC generator is a DC generator whose field magnetic winding is excited from an independent external DC source, example battery. So, here is the block diagram of separately excited DC generator which has been whose field winding is excited. This is the field winding which has been excited from an independent battery. This is the independent battery. Then comes the self excited DC generator. A DC generator whose field magnet winding is being supplied from the output of the generator itself is called a self excited generator. Here in this case of self excited DC generator, the only difference is the excitation is made self, that is we do not have any battery powered outside equipment to excite the field. There are three types of self excited generators available depending upon the manner in which the field windings are connected to the armature windings. They are series generator, shunt generator, compound generator. Series generator. In series wound generator, the field winding is connected in series with the armature winding. Figure 1.17 shows the connection of series wound generator since the field of series wound generator. Since the field winding carries the whole of load current, it has a few turns of thick wire having low resistance. Series generators are used for specific purposes, example boosters. In this type the voltage increases as the load increases. Let me zoom it on. So, this is the structure of a series wound generator. This is the armature, whereas the series field is connected in series with the armature and then the load. Here the armature current IA is same as the series field current, because the load current, armature current and the series current all are same. The terminal voltage V is equal to generated voltage E g minus I into R A plus R S E. So, this R A is the armature resistance, R S E is the series field resistance. Then the power developed in armature is given by the product of the generated voltage and the armature current. Then power delivered to the load is equal to V I A or V I L, because I A is equal to I L in the case of a series wound generator, because whatever current which flows through the armature is flowing through the series field also, the same current is flowing through the load also. Then comes the shunt generator. In a shunt generator, the field winding is connected in parallel with the armature winding. Here, the terminal voltage is applied across the field winding. The shunt winding has many turns of fine wire having high resistance. Therefore, only a small part of armature current flows through the shunt field winding and rest flows through the load. So, let me zoom this on. So, this is how a connection of shunt wound generator will look like. So, here is the armature, shunt field is connected in parallel to this armature core, and so as the load as well as the shunt field are connected parallel to the armature. So, whatever current which flows through the armature splits into two, one is the ISH, the other one is the load current. So, the armature current is a algebraic sum of the shunt field current and the load current IL. So, IA is equal to ISH plus IL. Figure 1.18 shows the connections of DC shunt generator. Shunt generators are used for lighting and power supply purposes. These are also used for charging batteries. The expression for shunt field current is equal to, as the shunt field is connected parallel to the armature. So, the terminal voltage, that is V by RSH, will give you the value of ISH, where V is the input voltage. The armature current IA is equal to IL plus ISH, terminal voltage V is equal to EG minus IARA. So, V is the terminal voltage, EG is the generated voltage, IA is the armature current, RA is the armature resistance. Then the power developed in the armature is equal to EG into IA, whereas the power delivered to the load is the terminal voltage into the load current. Then comes the compound generator. In a compound wound generator, there are two sets of field windings on each pole. One is in series and the other is in parallel with the armature. There are two types of compound wound generator. One is a short shunt compound wound generator, the other one is a long shunt. In short shunt, only shunt field winding is in parallel with the arm winding as shown in figure 1.19. Here the series field current ISE is equal to IL, that is the load current and the series field current are same. Shunt field current ISH is equal to V plus ISE RSE divided by RSH, where ISE is the series field current, RSE is the series field resistance, and RSH is the shunt field resistance. The terminal voltage expression is given by V is equal to EG minus IARA minus ISE RSE. The power developed in the armature is same as that of the previous one, which is EGIA, and the power delivered to load is equal to terminal voltage into the load current. Then comes the long shunt. In this, the shunt field winding is in parallel with both series field and armature windings as shown in figure 1.19. The series field current ISE is equal to IA plus IL plus ISH, where IA is the armature current, IL is the load current, ISH is the shunt field current. The shunt field current expression ISH is equal to terminal voltage V by RSH. The terminal voltage V is equal to EG minus IA into RA plus RAC. The power developed in the armature is same as that of the previous short shunt, which is EG into IA. Power delivered to load is given by the expression V into IL. Here are the diagrams of short shunt and long shunt. Here you can see here the difference between short shunt and the long shunt compound generators constructional wise. So, here the armature is not at all connected with any of the field windings in series, RSH is in parallel. Similarly, this RSE, that is series field resistance, is connected to the load in series, whereas here you can see the difference. In long shunt, here you can see this shunt field resistance is connected in parallel to the load and armature, whereas the series field resistance is connected in series with the armature, whereas here it is connected in short shunt, it is connected in series with the load, here it is connected in series with the armature. That is the only difference. In this type of DC generator, the field is produced by the shunt as well as series winding. The shunt field is stronger than the series field. If the magnetic flux produced by the series winding assists the flux produced by the shunt field winding, the generator is said to be cumulatively compounded generator. On the other hand, if the series field flux opposes the shunt field flux, the generator is said to be differentially compounded. Then we will move on to a very important topic on building up of EMF, electromotive force, in a DC self excited shunt generator. In self excited DC generator, the field current is initially 0, as the voltage generated is 0 at the time of starting, but the core material of the field will have some residual magnetism which helps in generating process of the EMF. Here you can see when the armature is rotated, this residual magnetism induces a small EMF in the armature called the residual voltage. This EMF is shown as OA in figure 1.20. Let me zoom this. You can see here. Even when the field current, right, even when the field current is 0 here, you have certain voltage. This is OA. This OA is called as a residual magnetism. Because of residual magnetism, you have this induced EMF OA. Even when field current is 0, you have a voltage built up across the armature which is OA. This is due to the residual magnetism. This small EMF produces a field current equal to OB dash. So, this is OB dash. Now, the flux produced by the field winding increases. This increased flux increases the EMF to B dash C, and this increased EMF once again increases the field current to OD dash, which in turn increases the EMF to D dash E. This process is cumulative and the EMF across the generator builds up. The curve obtained during this process is shown in figure 1.20. This curve cuts the field resistance line at point P as shown in figure. We will see it here. You can see here the point where, so this is the field resistance line. So, this is the field resistance lines O, D, F, H, M is a field resistance line which is going to cut the characteristic curve exactly at this point P. So, at this, after this point P, even when the field current is increased, you can see here. So, this is x axis is field current, even when the field current is increased beyond the point P, the voltage will remain constant. So, it does not have any impact on the developed voltage even when the field current is increased beyond the value, beyond the point P. It is due to the saturation of magnetic poles. Thus, the building up of EMF in DC shunt generator goes up until the curve cuts the field resistance line. At point P, maximum EMF will be induced and thereafter it remains constant irrespective of whether we increase the field current or decrease it. If we reduce the field resistance, the slope of the resistance line OR decreases. Hence, maximum building up of EMF goes up to R in the EMF curve. If the field resistance is increased further, the slope of the field resistance line will be increased, thereby decreasing the maximum induced EMF. Then comes the no load characteristics of shunt generator. As the name implies, this characteristic curve shows the performance of DC shunt generator under no load condition. That means load current is equal to 0. The curve drawn between the generated EMF and the field current is called no load characteristics. No load characteristics is also known as magnetic characteristics or open circuit characteristics. Here you can see figure 1.21 shows the experimental setup of obtaining no load characteristics. Here you can see here, so enlarged vision of the setup for obtaining no load characteristics. So, this is the input power supply for this prime mover. So, this is the prime mover input supply, then DPST switch, and the motor is connected through a 3-point starter, and the prime mover is mechanically coupled. So, this is the mechanical coupling. The prime mover is mechanically coupled to the generator here. Here is a generator, and then voltmeter is connected across the armature, and then ammeter and field. In this experiment, the prime mover, that is the motor coupled to the generator, is started with the help of a 3-point starter. Then the motor is made to run at rated speed by adjusting the field rheostat of the motor. When the generator runs at its rated speed, field circuit is disconnected by opening the switch. So, here is the switch. So, here is the switch, you can see this is the SPST switch, single pole single throw switch. This is being opened when the generator attains the rated speed. Then the reading of voltmeter across the armature gives the residual voltage. Then the switch is closed and the field current through the field winding is increased from 0, and the EMF induced for each value of field current is noted. Now, the characteristic curve is drawn between the induced EMF and the field current. Now, the induced EMF of DC generator is given by the expression Eg is equal to P phi Zn divided by 60A, where P is the number of poles of the DC machine, phi is the flux in Weber, Z is the total number of conductors, N is the speed in revolutions per minute, then 60A, A is the parallel path. If speed is constant, then the above equation becomes Eg is equal to K into phi, because this P number of poles is going to be constant for a given machine, number of conductors will not vary, it is kept constant for a given machine, then speed is also constant. A, the number of parallel paths will depend on the number of poles in a lap winding, and A is equal to mere a number, that is 2 in the case of wave winding. So, A also remains constant for any lap or any wave winding configuration. So, we can simply make this expression Eg is equal to P phi Zn divided by 60A into, so the entire expression boils down to a single expression K into phi, because phi is the only variable quantity. So, the magnetic flux is the only variable quantity in this expression, where K is constant. Here you can see, hence the EMF is directly proportional to the field current, that is Eg is proportional to phi, but the magnetic flux depends on the field current. The magnetic flux is directly proportional to the field current. If field current is more, the magnetic flux will be more, and vice versa. Therefore, I can say Eg is proportional to, instead of Eg is proportional to phi, I can say Eg is directly proportional to the field current If. The field current increases along the straight line as shown in figure 1.22. So, this is figure 1.22. The field current increases along the straight line as shown. If the field current is increased beyond a certain level, the field magnets gets saturated. Therefore, the induced EMF will not increase in linear proportion to the field current. Instead, it increases along the curve CD as shown in figure 1.22. Let me zoom this on. You can see here, right. So, during the initial portion of the curve up to OC, you can see here. So, this is the linear portion, this is the linear variation. Up to this portion OC, whenever the field current is varied proportionately, so the induced EMF across the generator, induced EMF is also varying proportionately, linearly it is varying with the field current. Once it reaches C, so here comes the magnetic saturation of the poles. Once the magnetic saturation of the poles come into picture, then after this, even if you increase the field current beyond this point of G, nothing will happen to this induced EMF. It is not going to vary linearly, because it is deviating. You can see the curve here, up to this point it is linearly varying. After the point C, once the field current is varying, it is taking a different route altogether. So, it is not linearly varying, because magnetic saturation occurs after this point C. Then comes the definition of critical field resistance. The field circuit resistance plays a major role in building up of EMF in a DC generator. If the value of field resistance is too large, then it will not allow sufficient field current to flow through the field winding to build up EMF. Therefore, the field circuit resistance must be smaller than a value called critical field resistance. Critical field resistance is defined as the highest value of resistance of the shunt field circuit with which a DC generator can build up its voltage. Beyond this value of resistance, the generator fails to build up voltage. The value of field resistance represented by the slope of the tangent to the OCC curve is known as the critical field resistance for a given speed of rotation. The value of critical field resistance is calculated by drawing a tangential line to the no load characteristic curve as shown in figure 1.22. The slope of this tangential line gives the value of the critical field resistance. That is, when once you draw the slope for this, once you draw a tangential line to the curve, and the particular Eg divided by this field current will give you the value of resistance called as critical resistance. Then comes the condition for buildup of EMF of a self excited DC generator. Number 1, there must be some residual magnetism in the generator poles. The field coils should be connected in such a way that the flux produced by the exciting current flowing through them must be in the same direction of residual magnetic flux. In a DC shunt generator, the field resistance must be less than that of the critical field resistance. Point number 4, in a DC series generator, the external load resistance should be less than the critical field resistance. Causes of failure to build up EMF and the best possible remedies. Number 1, no residual magnetism. So, this is the cause of one of the causes of failure to build up EMF. So, while starting a DC generator, there must be some residual magnetism in the magnetic poles of the generator, otherwise the generator will not produce EMF. The second cause of failure to build EMF is reversal of field connections. Due to residual magnetism, there exists small voltage called residual voltage in the generator. This voltage produces a field current in the field winding. If this field winding connections are reversed, then the field flux would destroy the residual magnetic flux, hence the generator fails to build up voltage. Third point is high field resistance. For DC shunt generator, if the field resistance is higher than the critical field resistance, then the generator fails to build up the voltage. Secondly, for DC series generator, if the load resistance is higher than the critical field resistance, then the generator fails to build up the voltage. Number 4, the other factors: open circuit or short circuit in the field, or armature circuit, loose brush connections or contacts, dirty or severely pitted commutator. So, these are the possible remedies which we can think of. Number 1 is, at the time of starting of generator, if the poles have no residual magnetism or the field winding connections are reversed, then the field winding must be connected to a DC source for a short period to magnetize the poles. This process is called as flashing of field. Number 2, in case of DC shunt generator, check the value of field resistance and ensure that its value is less than the critical field resistance, and in case of DC series generator, ensure that the initial value of the load resistance is less than the critical field resistance. So, before concluding this session on DC generators, let us have a quick recap of whatever we have learnt in this session. We have seen the classification of various DC generators and the structure and functionality of long shunt DC generator, short shunt DC compound generator, all those things, and we have seen what are the causes for non build up of EMF and then the possible remedies also. Thank you.